In the previous video, we discussed at length protecting groups and deprotecting groups, the ideas behind them, and the specific molecules we're going to use to protect and deprotect alcohols when we do Grignard reagents. And we also looked at this specific problem, at least the first part of 1318, and we saw how there was a part of the molecule that was the same in both of the reagents and the products, and there was a part that was different. The part that was different had a bromine to begin with, and to end with, it had a new carbon-to-carbon bond. Now, both of those features suggested a Grignard reagent. So we know from that we're going to have to do a Grignard reagent here. Now, in this video, I'm just going to walk through using protecting and deprotecting agents. And I will not, in this video, explain the concepts behind them, because that was done at length in the previous video. So if I use reagents here that don't have any meaning to you, or if I say anything that doesn't make sense, I strongly encourage you to go back and watch and digest the previous video on understanding or a few important concepts with protecting groups. Okay, so we know we have to do a Grignard reagent, but we can't just dunk some solid magnesium into a solution of this molecule, because although we would at first, that would allow us to turn this into a Grignard reagent, you might think you insert that magnesium in there, although you might be able to do that if you try to make that Grignard reagent by dunking some magnesium in there, the Grignard on one of the molecules will react with the alcohol on another one of those same molecules, right? When we draw these, we only draw one molecule, but of course we never just have one molecule. We have galaxies worth of them, even in just one drop. And so you'll always have more than one, and the Grignard reagent on one would react with the OH on the other. So you wouldn't be able to form the Grignard reagent from that molecule as drawn. So what can we do to form that Grignard reagent, which is what we know we need, because we start with a bromine and we end with a new carbon-to-carbon bond? We can protect the OH. In the previous video, we saw that to protect an OH, what you do is you add trimethyl silyl chloride, TMSCl, in the presence of triethylamine, ET3N. And like I said, if this looks completely foreign and meaningless to you, the explanation for this, what it's doing, what that stands for, what it means, the significance of it, how it's going to come back later, all of that was covered in that previous video. So if we add those together, that will take this molecule and protect the alcohol. So instead of just the H here, we will have the trimethyl silyl group. Actually, let me just write that so there's a little more room. Trimethyl silyl. And so now that is protected, so that is not going to react anymore. So then what we can do is we can make our Grignard reagent. So now we can dunk the solid magnesium in there. The Grignard reagent can form, and it won't react with what was the alcohol. It won't react with the TMSO, the trimethyl silyl protecting group. So now we have our Grignard reagent. And now we can do the Grignard reaction. So we can have this carbon nucleophile, right? This carbon now is a nucleophile. Really, if you wanted to think about what that looks like from the perspective of a mechanism, that bond is almost completely ionic, so that the carbon here would have a full negative charge, and the magnesium would have a full positive charge. Okay, so then what do we add? Well, we know we can react these Grignard reagents with aldehydes or ketones to make alcohols. So if we look back up here, what we want to add is this last group in yellow, that alcohol. Now notice, that has 1, 2, 3 carbons that we need to add, and the oxygen is on carbon number 2. So we can make an aldehyde or a ketone with 1, 2, and 3 carbons with the oxygen on carbon number 2. Now, we need to use an aldehyde or a ketone so that this carbonyl carbon is a really good electrophile, right? It loses its electron density to that oxygen above it, and it'll attract the wrath of that carbon nucleophile of the Grignard reagent. And these are all concepts that we've explored in previous videos, so I'm not exploring them at depth here. If all of this seems extremely foreign, I encourage you to master the information in previous videos for this chapter. So this nucleophile comes in, it attacks that, the pi bond breaks, the electrons go up on the oxygen, and you'll have this oxygen here with a full negative charge. So you just have to remember to stabilize that in a second step with a proton transfer from water, as we've seen several times in previous exercises. So what we end up with after that process, after those two steps, is now we have our 1, 2, 3 carbons, right? 1, 2, 3, 1, 2, 3 carbons there, and the oxygen becomes an OH. And so it's starting to look really similar to what we want, right? This is starting to look really similar to what we wanted up there. All we have to do is take off this protecting group. We have to remove that trimethylsilyl group, make it back into an alcohol, and then we're really home free. So we're going to deprotect that, and we saw in the previous video that you can deprotect these trimethylsilyl ethers with a fluoride ion that comes from TBAF, tetrabutyl ammonium fluoride. And we drew out the structure for that and explained what it does in that previous video, so TBAF. And what you end up with at the very end of that is you remove the trimethylsilyl protecting group, and you get back the alcohol. And that was what we wanted. So this molecule is the same one that we wanted to do. So overall, if you're like going into a kitchen and you want to make this transformation happen, you want to cook up, you want to whip up some of this molecule, what you need to rummage through and find in your cabinets is, first, TMSCl, trimethylsilyl chloride, in triethylamine. Second, so that'll give us this. Second, some solid magnesium. Third, so that gives us our Grignard reagent. Third, we need our ketone, the specific ketone that will add the right number of carbons in the right way. Here that was this 3-carbon ketone. This is actually acetone, which you might have used to take off nail polish before. And then in your fourth step, you want to follow that up with some water to stabilize the oxygen that has a negative charge in order to get the OH there. And then we just need to deprotect this group, take the TMS group off with TBAF. So tetrabutyl ammonium fluoride. And so this is sort of grandma's recipe for making this transformation happen. And like I said, I didn't explain the concepts behind how these protecting groups and deprotecting groups work in this video because we spent so much time on it in the previous video. Notice that in the middle, all you have is really just a Grignard reaction. You make a Grignard reagent, you react it with a ketone, and you follow it up with some water. Okay, so much for A. Now B is even trickier still. B is a little bit beyond the pale for our class. But I'll go through it anyway. Sometimes if you try doing things that are harder, then the things that you have to do seem easier by comparison, and you feel more confident about them. So even though this one is particularly tricky and harder than anything I would put on a test for you in this class, even though that's the case, let's go through it. Maybe it'll clarify other problems, make those seem simpler, and help to build your confidence in solving those. What you should notice here is that there are features that kind of repeat, just like in the previous exercise. You've got the 6-carbon ring with an OH on it. And you'll see that 6-carbon ring with the carbon and the OH on it reappears a couple times here. The other thing you should notice is that you start with a bromine, and what you end up with are new carbon-to-carbon bonds. So those features, starting with the bromine, ending up with new carbon-to-carbon bonds, those features should suggest to you that you're going to use a Grignard reaction. So you'll need a Grignard reagent. Okay. Even if you had no idea where to start here, you could see that you have a bromine here, you might be tempted to just turn that into a Grignard reagent. So take that, dunk some solid magnesium strips or chunks into this liquid here, and then you'd hope that the reagent you form the magnesium would insert itself there, and you'd have your Grignard reagent. But just like we saw last time, the Grignard reagent reacts with the alcohols, and like we saw in the last video. And so if you have even just a drop of this liquid, what you're hoping to get as your Grignard reagent, a drop would have hundreds of trillions of these molecules. The Grignard on one would attack the OH on the other, like we saw in the previous video. And so you wouldn't be able to form that Grignard reagent as written, because this alcohol is reactive. But what you can do to work around that and to be able to make the Grignard reagent is to protect this. And you protect alcohols from Grignard reagents by adding trimethyl silyl chloride, TMSCl, in triethylamine. And just like we saw in the previous exercise, and as we explained in the last video, the previous video, that turns alcohols into protected trimethyl silyl ethers, or ethers. Now that's a very unreactive group, and so now you can take this, dunk your solid magnesium strips or chunks in there, and that will allow you to create your Grignard reagent. Okay. So when we analyzed our original molecule, we knew that we had to do a Grignard reaction. The giveaway was we started with a bromine, we formed new carbon-to-carbon bonds. But, and so we formed that Grignard reaction here. But we didn't think about what that would have to attack. Now, if you look at what the groups that we haven't highlighted here, the new groups that are introduced, we have 2 carbons with an OH on just one of them. So you might be tempted to think, maybe I'll have an aldehyde, 2 carbons with the carbonyl on just one of them. The problem is, if you do this reaction, if you take this Grignard reagent and react it with this carbonyl, remember the carbonyl carbon is positive, the carbonyl oxygen is slightly negative. If you do that, so that this carbon attacks that carbonyl carbon, the pi bond breaks, electrons go onto the oxygen of the carbonyl. If you do that, you're just going to be left with an OH. You'll only be able to add one of these rings. Only one of these rings would add onto an aldehyde. But we want to add 2 of these rings. And this is where this exercise is particularly tricky. To add 2 Grignard reagents, you would have to use an ester. So instead of an aldehyde here, you would have to use an ester. Remember, that's where you have an oxygen to the carbonyl carbon. You have bonded an oxygen with another carbon attached. Now it could be any carbon chain over here. Just to keep things simpler, I'm going to put just a methyl group. So this is an ester, where you have a carbonyl with an ether attached, with an oxygen bonded to carbons on both sides attached. That's an ester. Okay, and we introduced ethers in the previous video. Now the reason why this allows 2 equivalents to add is because the oxygen and carbon chain, the alkoxy chain there, can act as a leaving group. So see how this happens. Now remember, this bond between the magnesium and the carbon is really almost ionic. The oxygen, or the carbon there, has almost a full negative charge with the full lone pair, and the magnesium has a full positive charge, almost. And so this carbon nucleophile can swoop in, attack the carbonyl carbon, the pi bond breaks, the electrons go up, and you would have what's called a tetrahedral intermediate. So what you'd have here is you'd have a new bond to this, the other methyl group is there, the oxygen is there, now with a full negative charge, and the oxygen with the methyl group is there. So if you're trying to sort of see this with your eyes visually, you have these two carbons with the oxygen, that's this right here, and then you have that leaving group part, the OR group, this oxygen bonded to a carbon chain. That's what you get after the first attack. This oxygen here is very unstable, and so that slaps back down. To use these electrons, slaps back down, and the reason why the electrons are attracted to this carbon is because the carbon is losing electron density to two oxygens. So each of those oxygens is becoming slightly negative, and that carbon becomes really slightly positive. This unstable negative charge there can't handle the pressure. It feels the positive charge, and so it swoops back down, tries to create a pi bond, and kicks this other group off. And normally you don't think of oxygen compounds as a good leaving group, and they're not usually. The reason why this oxygen in green is able to leave is because even after it leaves, so that's going to leave, these electrons are going to become a lone pair on that oxygen, which now will have a full negative charge. Even after it leaves, this is just an oxygen with a full negative charge, and that's what this was. So really, those are about equally unstable, and they form a sort of equilibrium. So this reaction goes back and forth over and over again, but at any point, you will have some of these molecules here. But notice what's happened here. After that step, you've reformed the carbonyl. Now, instead of an ester, you have a ketone. The carbonyl carbon is still slightly positive, the oxygen is still slightly negative, and another equivalent of the Grignard reagent can attack. So this is a sort of note you would want to make. Put a star in your notes and say, when you can make, a Grignard reagent can attack an ester twice. So it'll add one version of itself to the ester, leave you with a ketone, and then a second version of itself can swoop in and attack what was the original carbonyl carbon. So you attack this, the pi bond breaks, the electrons go to the most electronegative place nearby, and you would have, and you would have this original molecule. We're going to break that pi bond. The carbonyl carbon is going to be bonded to another equivalent of this group. Now that will leave that oxygen with the negative charge, which we're used to after these Grignard reagents. You usually have that negative charge. And you stabilize that with a proton transfer from water. So you shake that up with some water. This steals one of the slightly positive hydrogens from water, and you have the same molecule, just without the full negative charge. Instead with a bond to the hydrogen. Now let's take a look at this. We'll compare this with the molecule we wanted to make. So way back up here, many moons ago, we wanted to make this molecule here. Notice this is essentially the same thing. There's just one thing we have to change, but you have the two rings, right, with the branches there. In between them, you have these two carbons with an OH on them. And you've formed the two new carbon-to-carbon bonds. So really the same thing. The only difference is that we have these trimethylsilyl groups where we want OHs. So we still have the protecting groups on. We just have to remove those protecting groups. And the way to do that is to use TBAF. So tetrabutyl ammonium fluoride. And that will take those TMS groups off and replace them with hydrogens. So we've got our alcohols again. And that would be the product that we wanted, the original product that we wanted. Okay, so let's stand back. Let's look at the larger picture here. Think about if we were going into a kitchen and we needed to rummage through all the drawers to figure out what we needed in order to cook this thing up on the right, what would we need to use? Well, the first thing we'd have to use is trimethylsilyl chloride in triethylamine. That will protect the alcohol group. Then we can create our Grignard reagent. So we'll have magnesium. Once we have the magnesium, we can take that and react that with an ester. So we can take that, react that with this ester here. And notice that this R group could have been anything. I just chose a methyl group to keep the molecule small and simple. This other carbon chain had to have 2 carbons so that it matched what was in what we wanted, the product that we wanted. So that's the third step. The fourth step is we would use another equivalent of our, Grignard reagent. So a second Grignard reagent here. So we would have that there. It's the second equivalent of our Grignard reagent, and that would attack the ketone that we form. Then we use water to stabilize the negative charge on that oxygen. And finally, we remove the protecting groups with TBAF. Tetrabutyl ammonium fluoride. So this is like Grandma's home cooking recipe for how to make this transformation happen. And so that would be the solution for this one. Now you notice it's 6 steps, but that means it's just 6 times the fun of a 1-step exercise. So what you've seen in this exercise, 13.18, is how you can use protecting groups to protect alcohols and then do Grignard reagents, create and use Grignard reagents, and then deprotect them. And it builds on the sort of concepts, this exercise, this video sort of applies the concepts that we laid a foundation for in that previous video. Now this is something that you'll want to complete in your homework and that you'll want to kind of understand and have a sense of. It's definitely something that appears on the MCAT and the PCAT and the DAT. But this is not something that, if you're very pressed for time right now, this is not something to prioritize in studying for this test. You'll definitely want to be able to do Grignard reactions and have Grignard syntheses, but there are going to be other things in this chapter that are very time-consuming and difficult that are more worth spending your time on. For example, synthesis questions, multi-step synthesis questions. And so don't get distracted by this exercise. Make sure you understand the basic concept, you're able to follow what I'm saying, you write down the work that I've shown in these videos, but don't spend too much time just on this exercise.